Nanoparticles have been a conundrum to the human mind since the Lycurgus cup in Roman antiquity. But how can we measure such particles? Can we squint to see them? Can we use a magnifying glass? What about a light microscope? A light microscope will magnify up to 1,000 times. However, this is still not enough to see the particles on the nanoscale. An electron microscope is even more precision, with 10 million times magnification. However, nanoparticles are from between 10 and 100 nanometers in diameter. For this, we need something more. What could we use?
Use the Force, Luke.
Ah, yes. The Force.
So, what is atomic force microscopy, or AFM for short? Well, basically, it allows us to measure very small things and then make a 3D image, which is precisely what we need for measuring nanoparticles. But AFM is not as simple as looking down a tube like it is with a light microscope. So, to start to understand AFM, it's probably best to start with a demonstration.
The force is strong in this one.
So, an atomic force microscope consists of a laser, a cantilever with a nanoscale tip across the surface of whatever you're trying to measure, and a detector. This surface rests on a silicon plate which is connected to a piezoelectric crystal, and when that is connected to an AC current, what it does is it moves the surface side to side and up and down.
This chip is typically made of silicon or silicon nitride and has a sharp apex measuring only nanometers across. It is this nanoscale chip that gives such a high resolution to the image and allows such a large magnification. This chip can be used in surface imaging by dragging across the material to be measured. To detect the surface of the material reliably, the cantilever tip has to be brought in contact with the surface, such that repulsive forces dominate and deflects the cantilever. If the tip is not brought close enough to the surface, an attractive force dominates, causing it to deflect towards the surface. The cantilever tip is moved across a small area of the material systematically in rows, such that it eventually deflects the whole surface. Here we have a demonstration of the optical lever in human size. Over there, that is the laser. My arm here is the cantilever, and this mirror represents the cantilever's flat surface on the top of the tip. The tip is under here, and this is the detector. As you can see, the laser is reflecting off the tip onto the detector. This blue thing here will represent a nanoparticle, and when the nanoparticle goes under the tip, it will cause the tip to deflect and cause a deflection to be measured on the detector. Here we go. Okay, it's moving under. I'm going to move it out again.
So the flexibility of AFM comes from its three main measurement modes, which can be swapped in between. So we just explained to you contact mode, but there's also tapping mode and non-contact mode. So in tapping mode, the piezoelectric crystal oscillates the sample up and down below the cantilever tip. And this allows us to measure the sample without damaging it or the tip. And it also allows us to measure samples with liquids on them without it, adhering to the tip. Non-contact mode, on the other hand, is pretty much the same thing. And so what it does is that the tip oscillates above the surface without touching it, and it measures the force of the intermolecular repulsion from which it derives the 3D topography.
This 2D image is of the nanoparticles on a mica surface. The large dots are likely to be dust particles, but the small dots in the top left could be the nanoparticles that we're looking for. This 2D image is of the silver nanoparticles on a silicon wafer. To the right, you can see some of the vertical cross sections. This image is a 3D dataset of the last 2D image. It shows the topography of the surface being examined. Therefore, AFM is a very useful technique since it provides us with the force to examine even the smallest of particles.